Water has saved more human lives than perhaps any other substance. Entire civilizations rose around reliable sources of clean drinking water, and modern sanitation transformed diseases that once killed millions into preventable problems. If there's one lesson we've absorbed, it's simple. Cleaner water is safer water. So the idea that water can become too clean sounds impossible. Yet under the right conditions, a person can become critically ill or even die after drinking water that contains virtually no harmful chemicals, no bacteria, no toxins, and no contaminants at all. At first glance, that seems to violate common sense. If nothing dangerous is dissolved in the water, what could possibly make it lethal? The answer reveals a misconception hidden inside the way we think about drinking water. We usually judge water by what it contains: microbes, pollutants, heavy metals, or chemicals. Remove those, and we assume the remaining liquid can only become safer. But the human body doesn't evaluate water that way. For your cells, the question isn't simply whether the water is clean. It's whether adding that water preserves the precise chemical environment they depend on to function. A glass of perfectly pure water can be harmless in one situation and dangerous in another, not because the water changes, but because the body's internal balance does. That means the real mystery isn't how pure water becomes poisonous. It's why a substance essential for every cell in your body can, under the wrong conditions, become the very thing that pushes those same cells toward failure. To understand how pure water can become dangerous, we first have to stop thinking of the body as a container that simply needs to stay full. Your body isn't trying to maximize the amount of water it holds. It's constantly trying to maintain balance. Every cell is surrounded by a fluid containing carefully regulated amounts of dissolved minerals, including sodium, potassium, and chloride. These electrically charged particles, known as electrolytes, allow nerves to fire, muscles to contract, and countless chemical reactions to occur. Just as importantly, they determine how water is distributed throughout the body. That balance is remarkably precise. If the concentration of these dissolved particles changes too much, water doesn't remain where it was. It naturally moves across cell membranes, flowing toward the side with the higher concentration of dissolved substances. This movement happens automatically. Cells don't control it. It's a consequence of basic physics. The body spends enormous effort preventing those shifts. The kidneys continuously adjust how much water and how many electrolytes leave in urine. Hormones regulate thirst, control water retention, and help keep the concentration of the blood within an extremely narrow range despite constant drinking, eating, sweating, and breathing. Most of the time, this system is so effective that we never notice it. A glass of distilled water doesn't immediately dilute your cells because it doesn't remain pure for long. As soon as it enters the digestive system, it mixes with salts and other dissolved substances already present in the body before being absorbed into the bloodstream. Under normal conditions, healthy kidneys simply eliminate the excess water while preserving the electrolyte balance your cells require. So, the purity of the water isn't the problem. The problem begins only when water enters the body faster than that balancing system can compensate. At that point, the chemistry that normally keeps every cell stable starts to change, and that's when clean water can become unexpectedly dangerous. The kidneys are remarkably effective, but they have limits. If water enters the body slowly enough, they can remove the excess while keeping the concentration of electrolytes almost unchanged. But if large amounts are consumed over a short period, or if the kidney's ability to excrete water is reduced, the bloodstream begins to change. The first substance to become dangerously diluted is usually sodium. Sodium is the most abundant electrolyte outside your cells, making it one of the main factors that determines how water is distributed throughout the body. As more electrolyte-free water enters the bloodstream, the amount of sodium doesn't immediately decrease. Instead, the same amount of sodium becomes dissolved in a larger volume of water. Its concentration falls. This condition is known as hyponatremia. The name sounds technical, but the underlying problem is surprisingly simple. The blood has become too dilute. That dilution creates a new imbalance. The fluid outside cells now contains fewer dissolved particles than the fluid inside them. Because cell membranes allow water to pass much more easily than most electrolytes, water naturally moves into the cells in an attempt to equalize the concentrations on both sides. Nothing is pushing it. No cell decides to absorb more water. It's simply osmosis, the spontaneous movement of water across a membrane toward the side with the higher concentration of dissolved substances. One cell swelling slightly isn't a problem. But when billions of cells throughout the body begin taking up extra water at the same time, the consequences become impossible to ignore. Most tissues can tolerate a modest increase in cell volume. One organ cannot. The brain is enclosed within the rigid walls of the skull, leaving almost no room for swelling. That single anatomical constraint turns a problem of diluted blood chemistry into a medical emergency. Most organs can expand at least slightly when their cells absorb extra water. The brain has almost no such flexibility. Every neuron and supporting cell sits inside a skull that cannot expand. As water continues moving into brain cells, the tissue begins to swell, but the available space remains essentially fixed. Pressure inside the skull starts to rise. That pressure creates two problems at once. First, swollen brain cells can no longer function normally. The electrical signals responsible for thought, movement, sensation, and coordination become disrupted. Early symptoms often seem surprisingly mild: headache, nausea, confusion, or unusual fatigue. But they all point to the same underlying process. The brain is struggling to operate in an environment where its cells have taken on too much water. Second, the increasing pressure begins to compress the brain itself. Unlike swelling in a muscle or under the skin, there is nowhere for the tissue to expand. As pressure rises, blood flow to parts of the brain can become impaired, reducing the delivery of oxygen and nutrients just when the tissue is already under stress. If the imbalance continues, the symptoms escalate rapidly. Confusion can progress to disorientation, seizures, loss of consciousness, and, in severe cases, fatal damage to the brain. The striking part is that none of this begins because water is toxic. The water is doing exactly what physics predicts it should do. Once the concentration of dissolved particles outside the cells falls too low, osmosis drives water inward. The injury is the consequence of where that water ends up, and the fact that the brain has almost no room to accommodate it. By this point, the original paradox looks very different. Pure water isn't dangerous because of anything it contains. It's dangerous only when it overwhelms one of the body's most carefully regulated systems, allowing a life-sustaining substance to disrupt the chemical balance that every cell depends on. By now, the original question has almost answered itself. A person doesn't die because the water is too clean. They die because the body's ability to maintain its internal chemistry has been overwhelmed. That distinction matters. It also explains why distilled or highly purified water is not inherently dangerous. If you drink a normal amount, your digestive system quickly mixes it with electrolytes already present in your body, and your kidneys remove any excess while keeping the concentration of dissolved minerals within a narrow range. For a healthy person, the water's purity is largely irrelevant. The risk appears only when that balancing system is pushed beyond its limits. That can happen after consuming unusually large amounts of water in a short time, during prolonged endurance exercise when sodium losses through sweat are replaced with water alone, or in certain medical conditions and medications that reduce the kidney's ability to eliminate excess water. In each case, the circumstances are different, but the underlying mechanism is the same. Water enters the body faster than the body can restore the balance between water and electrolytes. This is why doctors don't treat severe water intoxication by simply waiting for the extra water to disappear. The immediate problem is the dangerously low concentration of sodium in the blood. Treatment focuses on restoring that balance carefully, because correcting it either too slowly or too quickly can itself damage the brain. The broader lesson extends far beyond this one condition. We often think of health in simple terms. More water is better, cleaner is safer, less contamination is always an improvement. But biology rarely depends on extremes. It depends on balance. Every heartbeat, every nerve impulse, and every thought relies on countless chemical concentrations remaining within remarkably narrow limits. Water is one part of that system, not something separate from it. So the paradox was never that perfectly clean water becomes poisonous. The real surprise is that life depends not only on what we take into our bodies, but on how precisely the body maintains the relationships between all of its components. Water is essential because it supports that balance. And under the wrong conditions, even the purest water can disrupt the very chemistry that makes life possible.